Hi, I'm Chuck Lever. I want to thank the program committee for inviting me. I'm going to talk about TLS handshake for Linux kernel consumers. This is quite the opposite of the talk we just had in here, which was a very low-level hardware talk. This is from the other perspective that of a network application, or several of them, which I'll get into in a minute. So a lot of people helped me with this. I just wanted to say thank you to all of them. Now I'm hoping to start a dialogue. I don't mean this to be a one-way presentation, so I thought I would tell you a little bit about myself. I'm not really familiar, deeply familiar with the Linux networking community, even though I've been working alongside them in other capacities for probably 20 years. So in the hopes of finding some common language, these bullet points kind of explain who I am and what I do, what I've been doing. I have authored some internet RFCs, so I do understand a little bit about networking, maybe not at the deep level that many people in this room do, but so there it is. I probably should mention that I don't have a lot of computer security experience. Interestingly enough, even though I'm talking about TLS. So you may hear me say things that sound crazy, and that's usually because I'm just not well informed in a particular way. So what I want to talk about today is the thing that we built, why we built it, who we built it for, and maybe some itemization of future work. What I don't want to talk about today, I don't want to do a demo. I'm not prepared to do a demo. There are some other things on here that people have asked me about that I should put on here as a disclaimer. The bottom one, people ask me all the time, is this facility ever going to support TLS v 1.2? It can, but we don't want it to. So we say no. The other question that I'm asked frequently is this similar to KTLS in the sense that user applications will use this facility to perform a handshake? No. This is entirely to enable in-kernel consumers to perform handshakes. That is a facility that is missing and something that we need. So what are our use cases? Well, I've listed three here. The one that I'm probably most familiar with is the first bullet, which is Sun RPC with TLS. I co-authored RFC 9289 that describes performing remote procedure calls with encryption. You can also do host authentication with TLS using this, that's described in this RFC. But mostly what we wanted to do was make NFS traffic obscure to anyone who's monitoring the network, because the IETF has published a very, perhaps very well-known RFC that describes monitoring as an attack, one that we all have to defend against, and so. Most or all new protocol that comes out of the IETF has to have some form of encryption in it. And RPC is age old. I mean, it was invented in the mid-'80s. So that's something that I think has needed real encryption built into it for a long time, and that's what I set out to do. And it turns out at the same time, the folks in the NVMe community were also working on adding TLS support for when they're using NVMe on TCP. Certainly, it's not for use with the RDMA fabrics style of NVMe. We also take note that Quick v1 uses the TLS handshake as its basic security model, and so we count that as one of our use cases because it's going to be possible, we hope, for in-kernel quick, if it ever shows up, will be able to use this facility to do its handshakes as well. So anyone who's familiar with RPC might know that we've had GSS API for a long time to provide our cryptographic levels of security. And it certainly does have an encryption mode, curb5p. So why do we need TLS? Well, it turns out that curb5p doesn't work very well in certain environments that are actually quite common these days. And one thing we really wanted it to do was we wanted to offload the encryption and decryption in much the same way that TLS has offloaded that onto some network cards. I believe Chelsea and NVIDIA and Mellanox cards can provide an offloaded encryption and decryption. We cannot do that with GSS Kerberos because that is a per user, the key, the encryption key is a per user key with Kerberos. It's a per host key with TLS, which makes it a much better candidate for offloading. So as we're going about thinking about how to implement TLS support for something like SunRPC, we looked at various solutions, and one that stuck out for us was KTLS. KTLS has been available in the Linux kernel for several years. It's also in FreeBSD, and it's coming to other operating systems as well. But it provides the encryption and decryption piece of this. The other component, of course, is the handshake, which I'll get to in a minute. As you probably already know, I'm just reviewing this, maybe for my own benefit, it provides both a software and hardware implementation. So the software means that the host is doing the encryption and decryption, and hardware would be the offloaded style where the NIC is doing the encryption and decryption. We looked at several different approaches to doing handshake. The one that we focused on early was doing an implementation of TLS handshake in the kernel itself. And we were heavily discouraged against doing that. We looked carefully at the Tempesta implementation. We liked that a lot for a lot of reasons. One of which is we'd eventually like to be able to do the root file system with encrypted NFS or root file system on an NVMe device that's using TLS. And if the TLS handshake has to go to user space for that, that kind of puts us in a deadlock scenario more often than we like. So we really wanted to go with an in-kernel implementation, but the security community felt that handshake is something that needs to be done by a library. And so they really wanted us to do an implementation that did an upcall, that the kernel's involvement was as a consumer of TLS, the TLS record protocol, and not implement TLS handshake in the kernel. So one idea we had was to create a protected middle layer between the kernel and user space, basically an alternate address space that's not the kernel address space and not a user address space. That would be easy to call directly from the kernel. That looked like it needed a lot of infrastructure that we didn't really know how to provide. And then the third option is the bottom bullet point is the one we eventually chose, which is to pass open sockets to a user space library for it to use a off-the-shelf handshake implementation on that socket and then pass the socket back to the kernel. Our first crack at this was to use something that looked like accept. The kernel, the Netdev community didn't warm up to that idea at all. The second idea was to use call user mode helper and a keyring kind of arrangement. There are lots of arguments against doing that. And the third was to create a netlink protocol that would allow us to pass the socket file descriptor up to user space, and then we'll have a daemon that intercepts that and calls a library implementation of TLS handshake. and that's what we actually did. And the library we chose to use was GNU TLS. That's got a reasonable open source license, unlike OpenSSL. The GNU TLS license is compatible with the kernel's open source license. We just needed to sort of create the infrastructure and the netlink protocol to make this happen. So essentially what happens is a consumer says, I want a handshake, and then on this socket, and it goes to sleep. And the socket is passed up to user space. GNU TLS handles the details on that socket. It sets up the KTLS session details using set-sock-opt, and then wakes up the kernel consumer and says, go to town, the socket is ready for use. Slide 11, I updated this morning. If you're looking at an old version of the slides, the PDF slides, it might only have accept and done on it. I forgot to add ready. So there are basically three verbs, if you will, in this protocol. One is ready, one is accept, and one is done. Ready is a kernel call that basically is to the multicast group that's listening for handshake requests and says, please, there's a handshake request ready on a queue. Somebody do an accept. We did it like this because multicast groups allow the kernel to tell if someone's listening. If no one's listening, then the kernel can immediately say, there's nobody listening, so fail this handshake request immediately. Otherwise, there's someone somewhere that's listening and running and ready to do an accept. So the second step is accept. It takes the MC group, which identifies which queue the handshake request was done on. Right now, there's only one. It's just for TLS. And it does the handshake as I described. And then when it's finished and the handshake is either successful and we have a session, or it's unsuccessful, the user agent calls done, and that calls down to the kernel and says, here's the socket back. You can wake up the consumer. So you might be asking yourself, okay, that's all very clever. How do you deal with host authentication material? We support X509 certificates and pre-shared keys. We also need to deal with authority bundles and private keys. And all this stuff is typically stored in the file system somewhere. So what does the kernel know about this? Does it have to care? How does it pick which certificate or PSKs to be used for a particular handshake? Well, what we did was we set up key rings. And basically the key rings have this material on them, and the key ring is handed to the user agent as part of the handshake parameters. So the agent gets the socket file descriptor, and it gets either a cert, a private key, or a PSK, and it gets these out of key rings. Or a simpler model is that the agent actually has default X509 certificates and PSKs that it can use and read right out of the file, in which case you expect to be configured for just a single kernel consumer to use these. But if we have multiple, like we have NVMe and NFS both using this, then the kernel consumer is going to have to identify which authentication material that the agent's going to have to pick to use for the handshake. We have sort of in mind in the long term to use TPM to store certificates. We haven't really done any of this work yet, but we're thinking about that. And the interaction with the TPM would be something reads a cert out of the TPM into the key ring, and the key ring then hands it to the handshake agent to use. I think I described most of this, so here it is for reference on the slide. I'll skip over this. Future work, RFC 9289 describes DTLS, how to use DTLS for RPC. We haven't actually implemented because we're really mostly interested in TCP, not really UDP anymore. And as I mentioned, quick support is underway. We've been talking about session rekey. Right now, all we do is we do a handshake, and then the session key is basically used until the connection is broken. which means if a rekey is needed, one or the other end of the connection has to break the connection, and then a new session is established. But as I've described, these consumers are mostly all long-lived connection type consumers. Unlike web consumers, these are storage ELPs. They open a connection and use the connection for a very long time. And so we figured this is probably a good start. We don't need session rekey quite yet, but we do have that on the radar. I mentioned storing certs in trusted computing module. Again, it's planned, but we haven't actually implemented it. And I also mentioned handling TLS protection for root file systems, NFS root or NVMe TLS en route. So where can you get this? It is in the kernel. Now, I think it went in 6.3 or 4. Pieces of it went in 6.4, pieces of it went in 6.5. I'm not quite sure when the NVMe is going to show up. They're still, I believe they're still haggling over some fine points. And there is a quick prototype that is being worked on. I put the URL right here on the slide for people to look at. The user space component is called KTLS utils. It is now on GitHub, and people can have a look at that. Or if you don't really care to look at source code, it's already packaged and provided in Fedora, SUSE, and Debian. Okay. Get that man a microphone.
Where's that man? Oh.
Hi, I'm David. You mentioned that this is not, it's not for KTLS, but what's the reason for that? Could this be used for the handshake part of KTLS?
What do you mean not for KTLS?
I think in one of the slides in the beginning, you said this is for in-kernel consumers and not for KTLS.
They do use KTLS. I'm sorry I gave you that impression.
Oh, okay. Sorry, it might be misunderstanding.
Yeah, essentially so I did the RPC implementation, both the server and client, and basically it uses this for doing the handshake, and then the handshake sets up a KTLS socket and hands it back to the RPC client or server, and they treat it like a regular old TCP socket.
I see.
They're none the wiser other than the beginning and ending handshake that has to go on.
Okay. And then a separate question about TLS in general. What is the state of TLS offload? So in a lot of companies, we actually see we turn off TLS because it's such a performance drag. And we kind of, we have all sorts of different workarounds where we kind of go back into clear text. And obviously offload is a way to kind of push that out of the CPU. But I guess it's just as someone who's new to the space, what is the state of the offload and hardware support and whatnot?
Right. So that's a good question. And I've got a complex answer for you. We're being storage protocols. We're very
it's storage. Mm-hmm.
Yeah, we're very concerned about performance. We know that, for example, I'm going to do a little sidebar here, but I will get to your answer. We know that Microsoft is taking SMB to run on top of Quick. And with Quick, encryption is not an option. You basically have to use it. I mean, it's not optional. It's always on. I said that wrong. So we're kind of looking at and wondering, in most implementations, there is no support for quick offload. All of the quick encryption, decryption is going to have to be done on the host CPU. And so we feel like maybe that's not ready for the more data center-centric storage protocols like NVMe or NFS. But with TLS, the TLS record protocol can be offloaded. I mentioned two vendors that already do this. Chelsea does, and NVIDIA Mellanox have products that can do this today. And that's where we're hoping we can have performance that is in the same general ballpark as plain text. That was why I put the slide up about GSS Kerberos not having offload. We think offload is essential for making this perform as well, or nearly as well as plain text. Does that answer some or all of your question?
Yeah, thank you. Okay.
So I had one question. You had that three-way handshake over Netlink at the start. The multicast groups do not have any flow control. Does that first handshake occur for every connect that comes in? And if so, how do you handle if you're getting DOS attacked with TLS connections?
We've never gotten that far yet.
Okay.
So we need somebody smart to come up with a solution for us.
There is no, yeah, I mean, that multicast flow control is a, pretty much unsolvable problem.
Okay. Well, I mean, what may happen is one day we actually have real in-kernel TLS handshakes. That would solve that problem immediately.
Well, what would happen is you just what you probably would expect under a DOS attack, which is you're going to drop some of them anyway, which is probably the solution you'd come up with.
Yeah, there is a limit on the number of pending handshakes we can have. And yes, when that limit is exceeded, those handshakes fail and or are dropped. So there's a reliability problem there, but in both the NVMe and NFS cases, if the connection isn't successful, the handshake isn't successful, they will keep retrying until it is.
Carl, can we maybe see if there's anybody remote? Oh, okay. Yeah, there is a remote question. Can you see that, Chuck?
I see what kind of information is passed from the user space handshake agent back to kernel consumers except the key. Some information from handshakes is required for consumers on server side. For example, server name indicator. Okay, well, it's true. It is different on the server side than it is on the client side. Essentially, what is passed is the handshake agent actually uses set sock opt to prime the socket with the session information. So it works just like any user application that wants to use a KTLS socket. And then the done down call passes only the socket file descriptor number and a status code that says this handshake worked or this handshake did not work. SNI is handled in the user agent. That wasn't I'm not sure I'm answering your question about SNI though. If you have more details about that, go ahead and put that in the chat room.
Ivan, can you hear us?
SNI information actually is passed up from the kernel in the accept call. It's not passed down from the user agent. And I believe SNI is a client-side thing. Basically, on the client side, the information in the certificate has to match the name of the server, the host name of the server that the application was passed from the user. And that's how the certificate is validated, or one of the ways how the certificate is validated. And so interestingly enough, if the certificate doesn't contain, the server certificate doesn't contain the IP address of the server that the client used to connect, and that the client, for example, tried to mount that server by an IP address, the handshake will fail. So server certificates have to contain both the host name and their IP addresses. That's usually done by making a list and storing it in the subject alt name field.
Any more questions?
You had mentioned that you were planning on pulling the CA certificate from the TPM. Why not offload TLS completely to the TPM chip?
I'm not sure I'm smart enough to understand that question.
So the TPM chip itself should be able to handle all the TLS handshake and all of it itself, and just store the private certificates in the TPM itself in a way that no one can access. And so theoretically, instead of just storing the CA, you could say, put everything to the TPM, let the TPM handle TLS for me. And that's all done at a hardware level.
Sure, why not?
Okay.
I think that's a little bit above my pay grade. We do want to be able to store the certs in the TPM. I'm not sure I understand what it means for the TPM to actually handle the handshake. The handshake is done by a user library, so it's got to have the certificate material available to it.
Okay, yeah. What I'm saying is you replace the user library with completely a hardware-based solution in the TPM.
So I imagine someday in the future that the user agent won't have to run in user space. You can have one running in the kernel that is also listening on this netlink protocol. So it could be something like something that is able to pass the correct sequence of goat entrails and other magic to the TPM and make it do the handshake for you. But that hasn't been written or even imagined yet. But I think this architecture would allow you to do that.
Okay, thank you.
Yeah, yes. I'm sorry. It's TLS 1.3 support, right? Is there a key refresh at all that happens there, or is it?
So I did mention that briefly. We intend to support session rekeying and refresh, but we don't right now. As I said, the connections are pretty long-lived in terms of the actual, like NFS and NVMe doesn't open a lot of connections often. And so it just runs the connection until either end decides, you've exhausted your key space and you need a new one. So it just closes the connection and you get a new key and you go through a full handshake. Now, eventually, we're going to have support in the netlink protocol to say, instead of a full handshake, please do a rekey. Just, we already know who this is, do a rekey. We don't have that yet, but we are aware that might be something people might want.
Yeah, I think Nginx does what you say. It closes and then opens the connections again. Anybody else? Alex? No? Okay.
Okay, so I'll be here all week. If people would like to drill into any of this in a more detailed way, I'm happy to talk offline.